Hello everyone, I am Paul Chen from National Taiwan University. Today, I am presenting our work, Headwind, Enhancing Interpretation Experience in VR by simulating air drag during airplane motion. Locomotion is essential in VR to allow users to move their location without the limitation of practical position. For example, the most popular VR game in 2020, Half-Life Alyx. It supports 3 different types of VR locomotion. Find out the most popular locomotion in commercial games. We surveyed the top VR game recommendation list from 9 popular gaming and technology news sites. The result shows that most people chose teleportation as the default locomotion technique. It is about 4 times as popular as the second most popular technique, which is continuous locomotion using the trackpad on controller. Teleportations involves fast navigation with low VR sickness. However, it reduces immersions and increases spatial disorientation significantly. Dash technique adds optical flow during teleportation to provide a visual experience of rapidly moving from the current location to the destination. The term teleportation in our work is a locomotion technique in VR by pointing a target point and teleporting to the target. Now, we have to figure out what kind of the haptic feedback is the best to enhance the experience of teleportation. We conducted a formality interview study with 16 participants on the types of haptic sensation expected by users during teleportation. Participants were asked to play Half-Life Alyx, both blink and dash teleportation modes in counterbalanced ordering, followed by semi-structured interview. We grouped the interview response into the following 4 types. Results shows that most common sensation is wing, followed by acceleration, deceleration, and phase landing. Based on these findings, we present Headwind, simulate air drag to improve the experience of the most popular locomotion, teleportation. Headwind extracts airflow from the pneumatic system in the backpack to the nozzles mounted on the headset to provide a wing sensation to the face. To provide the best feedback, we follow the design flow. First, we recorded delta angle from a 12-participant study that plays 3 VR games. Results shows that 90% of all teleportation was within 27.1 degrees of the heading of the HND. Prior studies on humans' ability to identify directions of wind on the face have found that the absolute pointing error, without any visual direction, average is about 14.5 degrees. The 3 air nozzles we mount on our device can provide wind perception from about -45 degrees to 45 degrees. To provide a more suitable wind feedback to the player's face, we reference the design of the commercial nozzles. After a pilot test, we chose the nozzle like a disco ball, which has a 24 degrees spread angle. We actuate the different nozzles to provide a different direction of wind feedback. Headwind is a portable device. We chose the Penpal air tank as our high-pressure air source. The entire pneumatic system, with weight of 2 kilograms, fits into a small backpack. The capacity of this air tank can afford about 1,100 times teleportation. And the weight of the head-mounting device of the Headwind is about 122 grams. We could ensure that the air pressure from the nozzles to the face can be near mapped to the wind speed. We measure the wind speed with the anemometer to prove that the air pressure from the nozzles to the face can be linear mapped. To measure the airflow speed reaching user's face, we vary air pressure from 75 to 500 kPa, and measurements show strong linear correlation with airspeed. To model airflow speed and duration for teleportation, We conducted a 16-person user study using a methodology of participatory design and also collected qualitative feedback. We selected two settings for each parameter: slow speed, fast speed, short duration, and long duration. Participants have to experience the four kinds of combinations. Participants held a Xbox One controller in their dominant hand and used the button to adjust airflow speed and duration. A single arrow represents a user, and a highlighted arrow represents the general model. Both blink and dash mode increase the airflow speed and duration along with the interpretation distance. To understand how headwind affects the user experience of interpretation, we conducted a 24-person user study and compared headwind to the standard VR experience using within-subject study design. We developed a VR game using Unity that supports both blink and dash interpretation modes. Players were asked to collect 50 randomly generated target zones. Each participant should experience one of two interpretation modes, with and without headwind in counterbalance ordering. Participants experienced and selected one of three general models setting from the participatory design study. Wilkinson side rank analysis showed that headwind significantly improved realism, immersion, and enjoyment for both blink and dash interpretation modes, and significantly improved comfort for the blink mode. Overall, participants rated headwind to have higher realism, immersion, enjoyment, and comfort than the standard visual and audio feedback. Most participants were optimistic about the airflow feedback and commented that it was entertaining, realistic, and comfortable. In addition, the only participants that didn't prefer headwind commented that I expected the wind to cover the entire head and the direction of wind to be parallel when moving forward. These are related to using multiple nozzles to achieve a wider coverage area. Thank you for your listening.